Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. In this video, we're going to continue our discussion on logarithmic properties. We use those properties of logarithms in a setting that mimics what you're going to need to know in calculus and pre-calculus. So again, this is for college algebra, which is kind of the gateway into pre-calculus and then calculus. So let's take a look at this example. Expand and state the domain of the function. Now, when you see that word expand, really what that means is write this logarithmic function as the sum or the difference of more simple logarithmic functions. This is known really as a heuristic method because what's happening here is that you have to get used to what it means to have a simpler logarithm. A simpler logarithm, for example, if I gave you the log of, let's say, x squared y. All right, let's just take that as a simple starter example. If I want to expand that statement, then what I'm going to do here is I'm going to go ahead and use that sum property that we proved in the last video. I'm going to split this to the log of x squared plus the log of y. And then these aren't simple enough, actually. What you want to do is take any powers that are common to the argument of a logarithm and pull those out in front of the logarithm itself. This would get us to the most simple form of that logarithmic statement. We will have essentially rewritten that single logarithm as the sum of two logarithms, but they're simple logarithms. Now, to be honest, this is actually what you're going to be doing a lot in calculus. You need this idea of expanding a logarithm because it becomes very, very helpful for us when we reach a point in Calc 1 where we have to take derivatives. So let's practice that skill here. Our function is just the natural log of a product of two objects. And notice that I'm saying it's just a product of two objects. I'm not saying it's x minus 1 times x squared minus 4. The reason why is because you really want to just start looking at pictures as just that. These are two different pictures. I have a yellow picture, let's say, and a blue. Let's highlight this blue. I have a blue picture as well. All right. So using the property of logarithms, I know this can be written as the natural log of the first picture plus the natural log of the second picture. Now, I have to be honest with you, this is not completely done because we know from our algebra prereq that x squared minus 4 is factorable. This is a mantra that I state to my calculus students all the time. Always perform arithmetic before algebra, algebra before trig, and trig before pre-calculus, and all of that before calculus. So as you're working with this, you really want to, before even using logarithmic properties, you probably would have wanted to factor that x squared minus 4, taking advantage of your older prereqs first. I kind of waited until this moment to do it, but you could have done it from the get-go. All right, so we get to this point and notice I still have the product of two objects. This object right here and maybe a different color. Let's do green, and this object right here. So I'll split that logarithm up one last time. That'd be the natural log of x minus 1 plus the natural log of x minus 2 plus the natural log of x plus 2. Notice that our function has now been written in terms of simpler logarithmic functions. Let me also remind you, you cannot break these logarithms apart. that natural log of x minus 1 is just that, natural log of x minus 1. There's nothing you can do. You can't pull that apart or anything. You're stuck. Now let's go to the more challenging question. What's the domain of the function? And this is critical in calculus. So we know from our prerequisite video material that we've gone through, we've talked about domains of logarithms already. And we know from that material that the argument of a logarithm, this whole entire picture right here, has to be positive. So let me actually focus on that. I know that x minus 1 times x squared minus 4 has to be positive. Okay, so this requires a little bit of extra work on our part. But luckily, if you've been following this video series and you're in this college algebra course, or you're in a college algebra course, you will likely have already graphed polynomial functions at this point. Now let me just showcase this. This polynomial that you're looking at, which is supposed to be greater than 0, can be factored a little bit more, right? That's x minus 1. We actually already did it. It's x minus 1, x minus 2, x plus 2. And we want that polynomial to be greater than 0. There are two ways to solve a polynomial inequality. One is to create a sign chart. That's very algebraic, and that's fine. You could totally do that if you were taught that in your previous course. That's totally fine with me. But I highly recommend you do what I'm going to recommend you do, which is graph that polynomial. If I call this polynomial, so let p of x equal this right here. So I'm going to let p of x equal that. If I graph that polynomial, really what I'm asking is, when is p above the x-axis? That's really what this is asking. And it gives you practice graphing polynomials. So let's go ahead and do that. Recall from our polynomial material, which is in my videos titled Graphs of Polynomial Functions, and there are 1, 2, 3, 4, maybe 5 different sub videos there. Recall from that you would first plot the x-intercepts. And the x-intercepts here are going to occur when our polynomial is 0, or at the zeros is what we would say. And this polynomial is 0 at 1 because of this factor, at 2 because of this factor, and at -2 because of that factor. So those are the 3 places we'll have zeros: 1, 2, and -2. So let me plot those points. Here's a -2, here's a +2, and then we need 1. So I'll just plot 1 here as well. The next thing you're going to hopefully recall, actually maybe I should just graph in the y-axis. Why not, right? So here's the y-axis. Nobody's actually asking me to do this cleanly, so I'm not going to bother being super clean about it. But recall that you really want to note the overall degree of this polynomial. This polynomial is 1, 2, 3, third degree polynomial, which means that it has the following end behavior. It looks like a cubic, so it starts low and goes high, just like a cubic would. Remember, a cubic would do something like that. So this is what this polynomial is going to do. Now, if you're watching this and you're just going, oh man, this seems like a lot of work, then maybe college algebra is not for you, because you're going to have a lot of work as you move through the STEM fields. And you're going to have to remember all of this material, and you want to synthesize it, bring it all together, do as much as you can within a single problem. I think that's just so good as you're learning material, whether it's mathematics or a foreign language. You want to live, eat, and breathe that as much as possible. So let's see. We have zeros at 1, 2, and -2, and they're all multiplicity 1, which means that our graph, polynomial graph here, will go through each of those zeros like a line. Notice how I'm embedding review in this lecture, even though you're probably not prepping for a final exam yet or anything like that. I like including review material the entire course because it's so important for you to see you are going to be using this. So here we go. We have our graph. This is our polynomial graph right here. And now you probably have forgotten why we did this because it's very easy to forget why you're doing this. We're doing this because we want our polynomial to be above the x-axis. And if you look at this polynomial, it is above the x-axis on this interval right here and on this interval over here. The blue curve is above the x-axis on those two highlighted intervals, not including 1 or -2 or +2, because we want to be strictly above the x-axis. So this tells me when that polynomial is positive, and remember, we needed that polynomial to be positive because that was the argument of our logarithm. Notice how the road kind of wound around this foresty path of little turns and stuff like that to get us to our answer of what is the domain of this function. It's a long, windy road, but that's kind of part of mathematics. So the domain of f, I'll zoom in to state it here. The domain of f is the interval starting at, but not including, -2, climbing up to +1, not including that, and then gluing onto that via a union, the interval starting at 2, not including it, and climbing all the way to infinity. And just in case you've forgotten from your Algebra 1 course or Algebra 2 course, infinity is a concept. It's not a number, so you'll never include infinities. It'll always have a parenthesis there. So that's the true domain of our function. Now, you went through all that, and you might say, why didn't we just use our simpler version of our logarithms? And here is the sticky wicket with logarithms. When you work with logarithmic properties, you should always pay close attention to your original function. When I hand you a function, or your instructor hands you a function, they say, here's this function, that is the function. Whatever manipulation you do with it from that point forward is kind of you possibly screwing things up. When I say you, I mean me and you. We have made some mistakes here. Not a lot, but we've said that this function is actually equal to those 3 logarithms, and it is, for the most part, until somebody says, do they have the same domain? And in reality, they don't. And here's why I say that. If I handed you this function here, and I said, that's your function, what's the domain? You would say, well, I need x minus 1 to be positive. Oops. Let me write that down. So you need x to be greater than 1. And then you would say, oh, and I need x minus 2 to be positive. So x has to be greater than 2. And then you would say, I need x plus 2 to be positive. So x has to be greater than -2. And then you would graph out each of those intervals. X has to be, let me draw those numbers first of all. Here's 2. Here's 1. And then here's -2. So from this condition over on the far right, we're told we want x to be greater than -2. But simultaneously, from this condition right here, we also need, and let me use a different highlighter actually, we also need x to be greater than 1. Simultaneously, we need both those conditions to be simultaneously true. And at the very same time, we need x to be greater than +2. So we need x to be only in that group. So our x values have to satisfy all 3 of those highlights simultaneously. And there's only one area that simultaneously satisfies all those highlighted regions. It's the intersection of those, and it would be all of these x values right here. All of these x values are common to all 3 intervals. So that is actually the domain of our modified function. The domain would be 2 to infinity. And this is, so I'm going to say domain of f with a bar on it. And the reason why I do that is because that's not the domain of our original function. It's the domain of our manipulated function. And this is kind of the weird part of calculus, is that you're going to manipulate logarithms quite a bit. When somebody asks what's the domain, do not look at your answer. Look at your beginning to state the domain. Look at the original function and say, okay, I need that highlighted stuff right there to be positive. So I want all that to be positive. And this is the proper work. So now if you're asking or wondering, what is the domain of the original function? The domain of the actual original function is this right here. The stuff that we just created, I'll just point at it in red here, is not the domain of our original function. It's the domain of our manipulated part. And that's not what you would ever answer with. So just to let you know that when you manipulate logarithms, you kind of create restricted domains. You can meddle with the domain a little bit. And so just be very careful about that. When somebody asks for the domain of the function, look at the original function, not your manipulations. I really truly don't think that one example is very fair here, so I'd like to do a second example because, well, why not? Let's start by just answering the second half of that. State the domain of that function, because that's the safest thing to do, is start with the original function and just work with that domain. So we want x over x minus 1 to be positive. Whoops. Again, you could go ahead and make a sign chart if you want, but I'm actually going to graph a rational function. It's really good to just get that practice. So I'm going to let r of x equal x over x minus 1. Trust me, the more that you practice this, the faster you'll get and the easier it will be for you when it comes to an exam or a final exam. When your instructor says, hey, I need you to graph this rational function, you'll be like, man, I've been doing it the entire time when I worked with logarithms and had to find their domains. I was solving rational inequalities. We're going to graph that rational function and we're going to find out when it's above the x-axis. Again, because we want this rational function to be greater than 0, so above the x-axis. All right, so let's see, x-intercepts. And by the way, I do have videos on rational functions. It's actually a whole video series called Rational Functions. And then there are 5 sub videos on a brief review of rational functions, finding domains, identifying vertical and horizontal asymptotes, finding slant asymptotes or oblique asymptotes, and finally graphing rational functions. So if you need a review of that, please go check that out. But the x-intercepts occur when y is 0 and y is 0 when the numerator is 0. So x-intercept occurs when x equals 0. The y-intercept occurs when x is 0. And if x is 0 in this statement, well, you have 0 over a negative 1, which is 0. So my x and y intercepts are identically the same here. And let me clean that up. That 0 is not good looking. All right. Next thing you do is the vertical asymptote. That's where you divide by 0 essentially after you've simplified the fraction. So that fraction is totally simplified. We see we have division by 0 at x equals 1. Also note, it's odd multiplicity. And I might as well note the x-intercept is multiplicity 1 as well. That's the power on that. And finally, the horizontal asymptote. And again, if you need the review of that, please go watch the video. But the horizontal asymptote, because the powers between the numerator and the denominator are the same, they're both degree 1 polynomials. You take the ratio of their lead coefficients, 1 versus 1. And so the horizontal asymptote would be y equals 1. Again, if you're staring at that going, man, this is too hard, or that's too much work, I'm telling you, math is probably not for you. You need to really get in the habit of taking your time with the problem and being willing to work. All right. So let me go ahead and graph out the x-axis and the y-axis. We'll plot our horizontal and technically vertical intercept. And I'll graph out the vertical asymptote. I'll graph out the horizontal asymptote. And this is one of those rare cases where it's hard to know when you start graphing this if it's going to move up or it's going to move down. It's actually going to move up here when it goes to the left because it'll want to approach this horizontal asymptote. So I know that. And then as it crosses this horizontal asymptote, horizontal intercept, because it's multiplicity 1, it goes right through it. It'll want to approach this vertical asymptote. And let me go ahead and draw that a little deeper. And then remember, the vertical asymptote is multiplicity odd. So the behavior on the left side is opposite the behavior on the right. So there we go. That's the graph of the rational function. Again, to review that, please watch my videos. But we want to know, when is that blue curve above the x-axis? Easy answer now. All of these x values and all of these x values. That's when my blue curve is above the x-axis, from negative infinity all the way up to 0, not including 0, union, pick up at 1 and go to infinity, not including 1 because that's a vertical asymptote. And that is the domain of our function, which I don't even remember the name of it, f. It's the domain of f. So all of that work was pre-work before expanding this function because they asked for the domain. If they don't ask for the domain, don't bother. It's totally fine. It's not that big of a deal. Most of the time they won't. They're just going to say expand this logarithm. But I like to sneak in this review. So let's go back to expanding this logarithm. It's actually super fast considering all the time we spent on this. It is a numerator, the logarithm of a numerator over a denominator. And so you can break that into the logarithm of the numerator minus the logarithm of the denominator. Notice the critical aspect of this problem, which was expanding this logarithm, is actually super fast. All right. There's nothing else you can do with that. That's completely expanded, totally done. And we also stated our domain in the process. Again, I really would like to drive home the fact that you need to practice graphing. If I'm not your instructor will thank me or thank you for practicing graphing. You really should do it. Now we're to the nuts and bolts of it right here. Notice that I didn't call this f of x for a couple reasons. One, I don't want you to find the domain. Two, it's not a function of x. It's a function of x, y, z, and t. So that would be a weird problem. So instead, I'm just saying expand this logarithm. And the practice you get here is incredibly important for calculus because, well, it just is. I'm not going to explain why. But we know we know all the properties of logarithms at this point. The first thing I would highly recommend doing is rewriting this radical as an exponent. Now, there are in calculus some instructors that want you to work with radicals, and I'm very much against that. I'm absolutely against working just strictly with radicals. I think radicals are an older notation. You really want to let go of those as you enter into calculus, and you want to write everything with rational exponents. So let's go ahead and pre-work this problem. And I want you to know, whether you like me or not, everything I'm telling you is to get you to be the most successful student you can be so you can succeed in your next course and into calculus. So I may sound like I'm a stickler on certain things, and I'm okay with that actually. Totally fine with that, because in the end, you will be a stronger student for it. So in this case, I highly recommend taking that fourth root and rewriting it as a 1/4 power. The interior, or the argument of that, or what we would call the radicand, would still be x squared, y to the third, and I'm going to go ahead and write that square root of z times the square root of t as z to the 1/2 And, well, z times, sorry, t to the 1/2, all being raised to the 1/2. Let me state that again because I sort of just spoke over myself a little bit. So we have a square root on a picture. Square roots are half powers. So that's actually the half power of z times the square root of t. That's exactly what we have here. Half power of z times the square root of t. But the square root of t is also a half power. It's just a half power on t. That's what we have right there. That's what I meant to say. In the denominator, well, there's nothing much you can do. That's e to the 6th times the quantity x minus y and quantity squared. Do not multiply that stuff out. That would be terrible. All right, so I have a picture. Let me highlight the picture. I have this picture, and that picture is being raised to a power. So I can grab that power and pull it outside of this logarithm. I did not mean my ink to be that big. There we go. So I'm going to grab that power and pull it outside the logarithm. So now I have 1/4, let me scroll up a little bit, times the natural log of x squared y cubed times the quantity z times t to the 1/2, and that is being raised to the 1/2. This is all over e to the 6th times x minus y raised to the 2nd power. Now, technically speaking, I suppose in that step, I could have used a property of exponents here, or a law of exponents, which tells me if I have two numbers multiplying and they're raised to a power p, you can take that first factor and raise it to a power p times the second factor raised to the power p. I could have done that right here. So I will. I had, let me highlight it, this product raised to the 1/2 power. So in the end, that'll be z to the 1/2 times t to the 1/2 raised to the 1/2. But again, you guys already know this. If you have a base raised to a power and that is being raised to a power, you would multiply the powers. That is, powers to powers multiply. So this could be written as t to the 1/4 instead of 1/2 to the 1/2. T to the 1/4. It's just cleaning this up using easy algebra skills from Algebra 1. And now I want to draw your attention to a trick. I'm normally not a fan of teaching tricks because I would like you to truly understand things. But because you should already have a full semester of logarithms behind you, I don't feel bad teaching you a trick right now. Remember, we have this property. In fact, you know what? I'll go over to the page. Remember, we had this property right here, the log base b of m times n, and it splits apart into a summation. And this one right here, m over n, splits apart into a subtraction. Another way you could have seen that it splits apart into a subtraction is the fact that that n is in the denominator. And if that n is in the denominator, you're actually looking at the log base b of m times n to the -1st power. Because again, we have that property of exponents that if you have something in the denominator, you can move it to the numerator and throw a negative into its exponent. And of course, then we could use this property to break that apart. So this would be the log base b of m plus the log base b of n to the -1st. And then you could take that -1st power and pull it out in front of that logarithm. And you would get this result. And really what I'm trying to say here is, anytime you have objects in the denominator, they can be thought of as moved into the numerator with negative exponents, and what happens to them in the end is they become subtractions. So if I wrote down log base b of a, whoops, maybe I should not use, yeah, I'll just do capitals. Capital ABC over capital DEF. Okay. Well, the stuff in the numerator will all be positive logarithms. Log A plus log base B of capital B plus log base B of capital C. And everything that's in a denominator will end up being negative logarithms. Negative log base B of D minus log base B of E minus log base B of F. That is a trick, but it's really helpful in calculus, so I want you to get used to it now. So let's go back to that problem and use this trick. We currently have 1/4 times this natural log. As I just said, everything in the numerator is going to break apart into positive logarithms. Everything in the denominator will break apart into subtractions of logarithms. The one thing you really have to be very careful of here is this 1/4 is multiplying everything that you're about to do. It's 1/4 times a natural log of a bunch of stuff. So our answer will be 1/4 times a bunch of stuff. Let's go ahead and write out the bunch of stuff part. With the natural log of x squared plus the natural log of y cubed plus the natural log of z to the 1/2 plus the natural log of t to the 1/4. And now we'll switch to the denominator. So minus, actually write it right here, minus the natural log of e to the 6th minus the natural log of, it's a quantity, let me kind of clean that up a little bit, of x minus y and quantity squared. And this is all within this big old bracket. Now the idea is that you can, well, actually what we're being asked to do is expand the logarithm. So what we need to do is continue forward writing these logarithms in simpler and simpler forms. And that means just taking each of their exponents and pulling them out in front of their respective logarithms. And then we will pretty much, oops, aimed at the wrong spot there, will pretty much be done. So this will be 1/4 times 2 natural log of x. See how nice and simple that logarithm is? Plus 3 natural log of y plus 1/2 natural log of z. Let's see what else we have. Plus 1/4. Notice I'm not bothering highlighting that now. I'm just writing it. Natural log of t minus. So this is a property of logarithms right here. This is log base e of e to the 6th. Well, that is going to be the number 6. We should know that. So that's minus 6 there. And the last one, notice that entire picture has a power of 2 on it. I'll pull that power out in front of that logarithm. So I have minus 2 natural log of x minus y. And there's, again, nothing you can do with that natural log of x minus y. It is stuck the way it's written. Now, I will have students at this point that will ask, should I multiply that 1/4 back through to all of this stuff? And the answer to that is, I don't care if you do or you don't, honestly. I think it's just extra work if you did. So you don't have to. Frankly, all these would have 1/4 in common if you were to multiply 1/4 all the way through. So it's kind of nice to leave that factored out. Now let's switch gears. Let's combine logarithms. Notice this one is still asking us to state the domain of the function. So let's start with that. It's always good to start with the domain question because this is before we screw this up, essentially. So let's go ahead and answer the domain question. We need this argument right here to be positive. And we also need this simultaneously to be positive as well. Let me write that down. We need x squared minus 1 to be positive, and simultaneously x minus 1 to be positive. They both have to be positive. In other words, I can't have one be positive and the other be negative. That would be illegal. So let's go ahead and take a look at what satisfies those conditions. This first one is just a parabola shifted down 1 unit. It looks something like that. And I'm asking, when is it above the x-axis? And it is above the x-axis on this interval right here. So I happen to know, by the way, those x-intercepts are at 1 and -1. So I happen to know that this inequality is satisfied on -infinity to -1, union 1 to infinity. The other one's much simpler. Just add 1 to both sides, right? And so this one is satisfied only when we're on this interval, 1 to infinity. You need to find the intersection of those two intervals. Let me do this. You need to find the intersection of this interval and this interval, and that is going to be 1 to infinity. So I know the domain of this function is 1 to infinity. I cannot plug in, for example, a -3. While it would work in this to plug in a -3 for x, because I get 9 minus 1 or 8, and I could totally take the log of 8. I cannot plug a -3 into this guy, because -3 minus 1 is a negative number. There you go. So the domain of the function will be 1 to infinity. Now that that's out of the way, let's do the easy part. Combine these logarithms. And that really truly is the easy part. Remember, it's a subtraction here. So whatever logarithm is negative, its argument will go in the denominator when we glue these things together. And whatever logarithm is positive, its argument will go in the numerator when these get glued together. That's about as easy as it gets. It's going to be log of the numerator's x squared minus 1 and the denominator's x minus 1. Now remember, do some algebra. That is a difference of squares in the numerator, so it's an x minus 1, which will cancel with the x minus 1 in the denominator, and you'll end up with this. Still, the domain of this, even though it looks like the domain of this could be any x value greater than -1, it's not true. The domain is that right there, 1 to infinity. And this is the tricky bit, again, about logarithms in calculus. Somebody hands you a function, you manipulate it, and your answer, if you hand that to somebody else and say, oh, here's the function that somebody else handed me, they're going to think that the domain is going to allow you to plug in any values satisfying that inequality, which means they're going to assume they can plug in any x value greater than -1. You need to let them know, nope, 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 no. While this is not actually what they handed me something else. So you're not allowed to plug in 0 or a number close to -1. The domain of this is 1 to infinity. You have to tell them that, otherwise they're going to think they can illegally plug in anything from -1 to positive infinity. Finally, I want to talk about a problem like this. Often you're faced with very complex looking problems in mathematics, but if you're facing something this complex looking, it likely is not that complex at all. Let's go ahead and at least deal with some of the easy parts of this. For example, the log base 2, well, there's nothing I can say about that. That's just the log base 2 of the log base 5 of 125. We know what that is from properties of logarithms. 5 raised to the third power would be 125. So therefore log base 5 of 125 is 3. So that's a little simplification. Still not much of one, but it is a simplification. And also, you don't happen to know the natural log of 87.2 offhand. If you do, that's pretty awesome. You also probably don't know 1,000 digits of pi plus 1 offhand. If you do, that's weird. But you do know the natural log of 1. The natural log of 1 is 0. And any non-zero number raised to the 0th power, well, that's just going to be 1. So we have log base 2 of 3 times log of 2 divided by log of 3 plus some number to the 0th, so plus 1. Notice how the complexity breaks very quickly. Now, a lot of students will still stare at this and say, I don't know what to do from here. But remember, we have a change of base formula. I would like all of these logarithms to have the same base. So transforming them into base 10 would be awesome. And that's what we're going to do here. I know that I can rewrite this logarithm here as log base whatever I want of 3 over log base the same base of 2. So I'm going to write it as log base 10 of 3 divided by log same base of 2. Notice what we get in the end. I didn't need a calculator for this because there's really simply no need for a calculator. All those cancel, that becomes the number 1 plus 1. And this is just a fancy way of saying 2. Those problems I think are highly entertaining. It showcases a lot of skill, a lot of critical thinking, a lot of observational skill that you're absolutely taking your time with a problem and pausing before you're jumping through it. I really recommend that you do that. You practice that patience in mathematics and look at a problem, stare at it for a moment or two, and try to find things that can be simplified. You might find that that helps out significantly, as it did here.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much. That isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.